Hey everybody, welcome back to chemistry. And so we are continuing on through chapter 4, and now we're at our final type of a reaction, which is called a redox reaction. So redox is short for oxidation reduction reaction. So you can recognize that you have a redox reaction when you are looking at the reactants of the reaction, and somehow you are able to notice that electrons are being transferred from one reactant to the other. So for that to happen, two things need to happen. One thing that needs to happen is that one of the reactants needs to lose electrons, and that reactant is said to undergo oxidation. The other thing that needs to happen is that the other reactant needs to gain those electrons, and when it does, it is said to undergo reduction. And so when you combine the pieces of oxidation and reduction together, you get redox. And so one of the things I want to do sort of to introduce this is to go over a very simple example of this. So I'm going to go over to the computer here. Okay, so let's take a look at what I think is a fairly simple redox reaction. And so we have a reactant here, which is zinc, and we have another reactant, which is copper sulfate. And then these reactants are reacting, meaning electrons are going to be transferred from one reactant to the other. And then when that happens, you get these products. You get zinc sulfate and copper. So let's look at this picture on the right of the reaction. So here on the left box here, we have the reactants. So these are reactants. And then on the right side, we have the products. So you'll notice that one of the reactants is zinc, and the other reactant is copper sulfate. Okay, so let's talk a little bit more about the copper sulfate. So the copper sulfate is ionic salt that is completely soluble in water. And so here in this solution is the copper sulfate. And so just a note here that what happens is copper sulfate completely dissociates into copper ions and sulfate ions. And it's really the copper ions in the water that make the solution blue. And the other reactant is just a piece of zinc metal. Okay, so if you let these two reactants sit together long enough, what will happen is that you will carry out a chemical reaction, and then you will see some changes. And so one of the things that you'll notice is that the blue color goes away. And so that might indicate that the copper ion for some reason is disappearing. Also, what you'll see is that on the surface of the zinc metal here, what you see is a solid accumulating on it, and this is copper metal. And so in this lower picture, you have sort of a nicer picture of that, and so you can see that this solid is kind of a blackish red color. And so again, the copper solid is a product, but also here zinc sulfate is a product. Okay, the sulfate ion is not important for this reaction, and so it will not be involved as a reactant, and it will not be involved as a product. However, the copper ion really is the ion that's important in the reaction. So I'm going to rewrite the reaction here, and so we have zinc solid and copper ion are reacting, and so what they'll produce as products, as you can see, are zinc ion and solid copper. So now what I want to do is kind of go back to the glass board and talk about why this is a redox reaction. Okay, so first let me go ahead and write out this reaction on the glass board. And so just to make my life a little bit easier, I'm going to leave out state symbols when I'm writing this. So we have zinc metal, and it's reacting with copper ion, and it produces zinc ion plus copper metal. Okay, and so to understand why this is a redox reaction, let's go ahead and evaluate the number of protons and electrons in all these species. And so here I'm going to write protons and electrons. So you can look up the atomic number of zinc, and what you'll find is that it's 30. That means zinc has 30 protons, so it has 30 positive charges, so I'm going to write 30 plus like that. Now, zinc metal is a neutral atom, so it should have as many electrons as protons, so it should be 30 negative. Okay, now the copper ion, if you look up copper's atomic number, you'll find that it's 29. That means all forms of copper, whether it be copper metal or copper ion, will have 29 protons. So it's going to be 29 positive charges. But here we're dealing with the copper 2+ ion. And so it's going to have 2 electrons less than normal. And so it's only going to have 27 electrons and 27 negative charges. Okay, now those are the reactants. Let's look at the products. Okay, in the product, we don't have so much zinc neutral metal. Instead, we have zinc ion. However, it's still zinc, and so that means it's still going to have 30 protons, so it's going to be 30 positive charges. Now, zinc ion, though, will it have 30 electrons? No, it's got to be deficient in 2 electrons, so there are 28 electrons here in the zinc ion. The copper metal here is going to have 29 protons and 29 positive charges. And then this is the neutral copper metal. And so this is going to have 29 negative charges or electrons. Okay, so I'm hoping you can sort of see why this is considered a redox reaction. And I think if you look at this carefully, that you can see that when you're going from reactants to products, you must have electrons being transferred from one reactant to another. So let's see how that's happening. So if you look at the reactant side, you can see that you're starting out with 30 electrons. But when you're going to the product side, you're down to 28 electrons. So it looks like zinc is losing 2 electrons as you go from reactants to products. Now, where are those 2 electrons going? Well, copper ion starts out with 27 negative charges, electrons, and then it picks up 2 to become 29 electrons. So the 2 electrons that are being lost by zinc metal are being transferred over to copper 2+ ion. So I'm going to write 2E- like that. Okay, so that identifies this as a redox reaction. So one of the things you're going to have to do whenever you see a redox reaction is you're going to have to identify the reactant as being oxidized, and you're going to have to identify the reactant that is being reduced. And so there are some simple rules for that. And so the rule I like is LEO goes grr. So LEO stands for loss of electrons, oxidation. GR stands for gain of electrons, reduction. So let's see which of these 2 reactant species is losing electrons, and that means it's undergoing oxidation or being oxidized, and which of these 2 reactant species are picking up electrons, meaning they're gaining electrons and they're becoming reduced. Okay, so what I'm going to do to sort of help me out is I'm just going to write out some what are called half reactions. And what a half reaction is you're just following one kind of reactant through to products. And so we're just looking at zinc here, and you can see in this reaction inevitably it becomes Zn2+, right? And then let's look at copper ion. That's the other reactant. So we have copper ion, which is Cu2+, and it's becoming copper metal. Okay, so now let's figure out which of these reactants is being oxidized and which is being reduced. So it looks to me that zinc here as a reactant must lose 2 electrons to become zinc ion as a product. So if it's losing electrons when you're going from reactant to product, that means it's being oxidized. And so the zinc metal here is being oxidized. Okay, so which reactant is being reduced? Well, GR, gain of electrons, is reduction, and so I think you can see is that the copper ion reactant is gaining electrons from the zinc metal reactant, and when it does, it goes to a product which now has 29 electrons, and so which is neutral and therefore will be a metal. So copper here is being reduced. Okay, so now I want to add a little bit more information to these 2 half reactions here. So here, again, the zinc metal is losing 2 electrons and it's becoming zinc ion. And so to indicate that the zinc metal is lost 2 electrons, you can think of it this way. It becomes zinc ion and then the 2 electrons are released. Okay, so I can write plus 2 electrons like that. Now, how about the reduction reaction? Well, we know here that copper 2+ is gaining 2 electrons to become copper metal. It's going to be gaining these 2 electrons. And so to indicate that copper 2+ is gaining 2 electrons, I'm going to put 2 electrons here like that. Okay, so far so good. So one thing you're also going to have to do is you're going to have to identify oxidizing agents and reducing agents. So this is a little bit tricky at times. And so let me explain to you how you do that. So there's a simple way of thinking about it, and then there's a little bit more complicated way of thinking about it. The simple way of thinking about it is this. The reagent or reactant that is being oxidized, that is the reducing agent. The reagent or reactant that is being reduced, that is the oxidizing agent. Okay? So sort of the way you can sort of think about that is that think of them as sort of, if you will, double agents, right? So even though zinc is being oxidized, it is considered to be a reducing agent. And even though the copper 2+ ion is being reduced, it is considered to be an oxidizing agent. So why this reversal? Well, let's think about what zinc is doing. So zinc is definitely losing 2 electrons, right? And so it's being oxidized. But here's another way you can think about this. Zinc is forcing its 2 electrons on the copper ion. So basically, you can see that the zinc metal is the agent for copper ion's reduction. So therefore, this is considered to be a reducing agent. Now here we have copper ions picking up those 2 electrons to become copper metal. So the copper ions are being reduced. So how do we think about this? Well, we can think about it as maybe that these copper 2+ ions are yanking 2 electrons off zinc. So basically they are forcing the oxidation of zinc. So here the copper ion is not only becoming reduced, it is also an oxidizing agent. Okay, so one of the things I want you to notice, which is kind of important, so when I identified what is being oxidized, what is being reduced, what is the reducing agent, and what is the oxidizing agent, it was only the reactants. And so here the products are none of those. So this really only applies for the reactants of the reaction. Okay, here I've sort of described in this slide what I just wrote out here. And so we're going to move on. Now there is another way of figuring out whether a reactant is undergoing oxidation or reduction. And so I need to sort of tell you about that method. And so the way we do that is by assigning something called oxidation numbers to these atoms or ions or molecules, and then following the changes of the oxidation numbers as we go from reactants to products. And so what I want to do is sort of assign these oxidation numbers. So what oxidation numbers are is that they sort of tell you whether the atom or ion maybe has an excess of electrons than normal. If so, it'll have a negative oxidation number. Or maybe whether it's deficient in electrons than normal, it'll have a positive oxidation number. Or whether it really has the amount of electrons it should have, it's a neutral species. If that is the case, then the oxidation number is 0. So let us go ahead and assign oxidation numbers to the reactants and to the products. And so zinc here as a reactant is a neutral species. And one of the things you'll have to memorize is that whenever you have a free element that is neutral, its oxidation number is 0. So I'm just going to indicate oxidation numbers here above these symbols here. Okay, now what is the oxidation number for the copper ion? So another thing that is helpful to remember is that the oxidation number for a monatomic ion will be the same as its charge. Now with charges, normally what you should write is the number first and then the charge next. But here with oxidation numbers, it's reversed. People typically write the charge first and the numbers next. So the oxidation number of the copper 2+ ion is +2. Now we have the zinc 2+ ion as a product, and so what's its oxidation number? It should be +2. Okay, what is the oxidation number of the product that is copper metal? It should be 0. Okay, so another way to figure out whether these two reactants is being oxidized is to find the reactant that is getting more positive in oxidation number. So let's go ahead and figure that out. So one reaction here is zinc, and it's becoming as a product zinc ion. And then the other reactant is copper ion, and it is becoming copper. All right, and so I just kind of indicated that zinc here has an oxidation number of 0, and then the zinc ion is +2. And so with copper 2+ as a reactant, it starts with +2, and then it goes to 0 oxidation number. Okay, so again, the reactant that as you go from reactants to products is getting a more positive oxidation number is going to be oxidized. The reactant that's getting a more negative oxidation number is being reduced. And so one of the things I think you can see here is that because zinc is getting a more positive oxidation number, it is going to be oxidized. And so we've identified here this reactant of zinc as being oxidized. Okay, and then the copper ion is getting a more negative oxidation number. You're having a more reduced oxidation number, and so you can say that the copper ion is being reduced. All right, okay. So in this slide, I'm just writing out what I just described here. Okay, so a lot of times you're going to be given a chemical reaction that is a redox reaction, but the problem is the reaction may be a little bit more complicated than just having free atoms and ions, and so it may be more difficult to figure out what the oxidation numbers of the elements are. So let me give you an example of one of these kinds of reactions. And so here we have methane, and it's reacting with oxygen, and it's producing carbon dioxide and water. So one thing you see immediately is that most of the time with the reactants and the products, we don't have a free element. We do have a free element with oxygen, but here the methane and the other products are not free elements. Also, we don't have any ions here, so it may not be so clear what the oxidation numbers are. Now, oxygen here, because it's a free element, is going to have an oxidation number of 0. But one of the things you're going to have to learn is how to assign oxidation numbers for these elements in the compound. And one of the things you're going to learn in a bit is that when hydrogen is bound to other atoms in a compound, it has an oxidation number of +1. When oxygen is bound to other atoms in a compound, it has an oxidation number of -2. Okay, so this hydrogen here in water, because it's hydrogen bound to another atom in a compound, it also has an oxidation number of +1. Now, carbon, you'll learn, and you'll be able to figure out later on, has an oxidation number of -4. So the question is this: does this carbon have the same oxidation number of -4? And the answer is no. It has a different oxidation number. Carbon in this compound has an oxidation number of +4. So one of the things you can see is that for certain elements, the oxidation number can be different depending on the compound it's in. And so at this point, you sort of have to learn how to assign oxidation numbers. And so let's go to the next slide, and we'll go over that right now.